Okay, so we're talking about vector and scalar fields, AP Physics 1. Let's talk about scalar fields first. So when we talk about scalars, these are things we can measure that are simpler. They're simpler than vectors. And how are they simpler? Because they have magnitude only. And magnitude is a fancy word for you can measure them. There's only an amount. There's not a direction to them. So let's think about a scalar field. How would a scalar field look? So a scalar field might be, we might talk about temperature. Temperature is a scalar. And how could we create a temperature scalar field? So you might have, if you look in the room, and we have a space heater because it gets chilly in here sometimes. So here's our little space heater. Yeah, sometimes, like all of the times. And the space heater is radiating some heat and making it warmer near where the space heater is. And then it's colder kind of further away. And so if we create, this is creating a temperature field. And we could kind of track like, okay, well, let's look at like this location right here and that spot, and we could say, okay, well, that temperature is maybe 30 degrees Celsius, but then further away over here, the temperature is a little bit cooler, and so maybe it's down to 20 degrees Celsius. And then down here, maybe the temperature is a little bit closer to the thing, so maybe it's 32 degrees Celsius. And then right here, it's also 32 degrees Celsius. And right here, it's also 32 degrees Celsius. And it turns out that we can create this field where we look at getting close or far from the heater, and we have these values that are all kind of the same at certain distances from the heater. So if we were to say like, okay, let's connect these dots of 32s, like that, then we're getting this line of equal distance space from the heater where we have equal temperatures. And then we have like these lines might all be 30 degrees Celsius. These lines all might be like a 28 degrees Celsius until you get all the way out here and you have these points. They're like equal distance away from the heater, and maybe they're all cooled down to 20 degrees Celsius. And these lines then, these are called iso lines. Iso means same. So they're the same, and they're lines that have the same value. In this case, since they're temperature, they're all the same temperatures. And there's no direction to this. This is creating a field of all these points where you have points getting lower and lower in temperature. So you have like 32 degrees temperatures, then 30 degrees temperatures, 28 degrees, and then all the way out here to 20 degrees. And we kind of have this field that's radiating out from the heater going where the temperatures are getting lower and lower the further away you get from it. But there's no real direction to each temperature value. They're just the amount. And as you may know, if you know a little bit of science, you know that your temperature is just an average value of the motion of these molecules, or we would say the kinetic energy in each molecule of air that's moving around. So that's a scalar field. And so it doesn't really have any direction, it just has amounts. And if we look at a vector field, we could take a look at maybe the weird world of electricity. So vectors. Remember vectors, like from Despicable Me, you have vectors committing crimes with both direction and magnitude. Oh yeah. And so vectors have the two things. They not only have the magnitude like scalars do, but they also have a direction. Oh yeah. And so they ask the question not just how much, but which way. And so you have to draw arrows for vectors. And what we say with vectors is the longer, the stronger. The longer the vector, the larger the magnitude. And that's what I mean by stronger. If I say it like more an intelligent speak, the larger the magnitude of the value that you measure, and then the direction the arrow points is giving you the direction, obviously. Let's take a look at some weird stuff with electricity. Let's say that we have a point charge here, and let's give it like, you use Q for charges. So let's say it has a charge of 2 capital C's, and capital C's stand for coulombs. But we don't want to write that because it's going to get in the way of all our stuff. So it has a 2 coulombs of charge. And then let's make another charge, and let's put it maybe down here. And this one has a charge, a Q, and we'll make this Q2 to say it's a different charge from the other one. And this one has 3 coulombs. But the thing about electric charges is that they can have positive or negative charges. There's 2 flavors of charge out there in the universe. We'll say Q1 and Q2. And so what if we were asking ourselves, self, what kind of charge do these have? Like, is one positive and one negative, or are they both positive, or are they both negative? We would have to test this field, the field that they create. So we test it out. So how do we test it? We put a positive test charge somewhere. And you can remember that test charges are positive because if you write the word test, then you're writing pluses at the beginning and the end of the word for the T's. And so that reminds you that's positive. You can also squeeze in a little plus there in the E if you get really inventive there. So test charges are positive. So let's test the field and put a little test charge in here. Let's put it maybe right there. Boop. Here I am. I'm a little positive test charge. Yay. And so then let's see what happens to this test charge, and that'll tell us what kind of charges we're dealing with in the red and the blue. And so what you would see is you would see forces, pushes or pulls happen to that test charge, and forces have a magnitude and a direction, so they can be drawn with vector arrows. So let's say that we see this happen to it. From the Q2, we see that the positive charge, and you just draw the vectors right in the center and then point in the direction they would go. So it gets pulled towards this thing, and it gets pulled pretty strongly downward. But it doesn't go directly downward. When we watch it, it actually is going to go a little bit differently. It's going to, from the red charge, it's going to be pushed away. We find that it gets pushed away. But it's also farther away, and the red charge is not as strong, so the push isn't as strong. So it's only like that strong. Remember, with vectors, the longer, the stronger. So we're showing a blue vector that's much stronger than a red vector. And then how do we put these together? Well, to put vectors together, you do vector addition. And remember, you line them up head to tail. So this is the way they look when you draw them on top of each other. And then you can kind of predict that what's going to happen when you combine these, which you call the resultant of the two, is going to be something in between these two. A little bit more towards the blue side of things. So that's just a prediction there. Maybe it's going to be something like that. But let's determine that for sure. So what I'm going to do is I'm going to actually cut out this blue vector. I'm going to move it over so that we're doing vector addition. So vector addition is lining them up head to tail. And so I'm lining up the tail of the blue with the head of the red. And I actually lost a little bit of my blue vector there. So let's see if I can steal that up. No, it doesn't want me to. So I'm just going to get rid of that. And I'm going to draw it again. Boop. There we go. And so then I was pretty close, but not exact. So then I can put my resultant vector in purple, like from the beginning where we start to where we end, right there. And so what we see is, we see the test charge actually get pushed kind of down right, instead of exactly to the right and exactly down. It's somewhere in between. It's more down than right because the pull downward is stronger. And so this would be created by two vector fields, fields that have strengths to them, and that would be their magnitude, and they have directions. And we're adding together the field to find the combined effect of the field with this vector addition. And then if you wanted to actually, find out the real thing, if you had numbers, then you could you could use Pythagorean theorem using maybe A, B, and C, and we put these little arrows above vectors. So these are little force vectors, force vector A, force vector B, and force vector C. And C would be the resultant, so you could actually put a capital R in place of a C. We use that a lot of times for resultant vectors. You could use A squared plus B squared equals R squared. I know you wanted to say C squared, to find the actual magnitude of them. And then you would have to identify angles with a little theta maybe, a little theta there, to get your, and use SOHCAHTOA to get your actual direction to it. But we're not really interested in that right now. We're just interested in the difference between a vector and scalar fields. And so let's see if we can use this to identify what's going on with these two charged particles. So the test charge exposed what was happening. The test charge showed that it's pushed away from the red. And why would a positive test charge be pushed away from another charge? Because they're likes. And in electricity, we say that likes repel. But then opposites attract. It's like the main thing of most of chemistry and most of all of electricity, really. So if you get that down, you're doing pretty good. So likes repel, so these must be likes. So this must be a positive 2, and that Q1 must be a plus 2 coulombs. And the field then points the way that forces will be felt by the test charges. So we draw field lines. Field lines are not vectors. Field lines extend kind of infinitely far away, but we can't draw them infinitely far away, so we'll just draw like a long ways on the paper. And then you put arrows on the field lines to show that they point away from this positive charge. Away. Now let's look at the blue one. It was attracted to the blue one, so it must be opposites attracting. So we must have a negative charge down here. So this is a negative 3 coulombs for Q2. And then that field would point in towards things. So let's kind of like clean this up a little bit and create field lines that, it's like little sun rays. Now here's a little physics trick. Q2 is stronger. It has 3 coulombs versus Q1 has 2 coulombs. And so you draw more field lines to show that it's stronger. With field lines, you can't do longer equals stronger, like vectors, because they technically extend into infinity. And so we draw more. So around the red one, I have 1, 2, 3, 4, 5, 6, 7. So I should do more than 7. I have 1, 2, 3, 4, 5, 6, 7, 8. 8's good. Maybe I'll squeeze in a 9th one, maybe right here. And then you point arrows in to show that any test charge in any of these locations would be drawn in. It'd be attracted to the negative because test charges are always positive. And so that's why our test charge, or positive test charge, was attracted. Okay, so this is a force vector field. It's an electric field, and it creates electric forces, which we drew as vectors. And the closer the test charge is to the positive or negative charges, the stronger those fields will be. And so we draw longer vectors. So let's just see one last little bit here. Let's see what would happen if we put a test charge, instead of right where we had it before, let's put it in a different location, and let's see what happens. So let's put it maybe let's put it right over, and it's positive, so I'll make it a red, because I've done red and blue for my positive and negative stuff. So let's see what happens if I put my red test charge all the way right over here on the right. There it is. Boom. So what's going to happen? It's going to feel a strong pull to the left. Strong pull to the left. Let's make this force vector. Make it very strong. So real long. And it's okay if that arrow kind of bleeds into the picture there. So there's our strong force vector to the left. And then we're going to do a force vector that is going to be exactly away from the red. So it would be like exactly away in that direction. But it'd be much smaller because it's further away from the red. And the red is a weaker charge with only 2 coulombs versus the 3 coulombs of the negative. So it'd be small. little baby vector there. Boop. There it is. Just a little teensy. And how do we add these together? Well, we're going to draw them head to tail and keep the same directions. So maybe I'm going to do, let's do this. Let's steal the red vector. Whoop. And move this around. Oops, I accidentally stole too much. Let's just steal the red vector. Boop. All right, there we go. And let's move it over. So we add these head to tail, and so we put it just like that. Boop. And so we see that the resultant, which we'll do in purple because that's the way colors combine, is going to be from the beginning to the end. And so it's going to be mostly moving to the left because it's mostly attracted to the negative charge, but deflected a little bit downward because it's being repelled by the red positive charge. And so that's vector addition. You might see like the parallelogram method, so that if you're trying to draw this on paper and you can't just clip these and move them around, well, how would you do this? Well, you could draw, let's kind of give a little like nicer space here. So let's take my blue vector, which was like 1, 2, 3, 4 squares long, and is exactly to the left. Let's draw that here. And then let's do the red vector, which was kind of like cross-cutting down and right, and let's draw them head to tail, and that kind of cross-cut and touch the middle of a square there. And then let's reproduce these to make a parallelogram out of them. So, and I stole this from Paul Hewitt's. There we go. Sorry, I'm thinking to draw here. Conceptual physics book shows this nicely. Paul Hewitt's conceptual physics book. So then we have a parallelogram there, and then we can draw from the beginning to the end to show the resultant vector. The cross cuts, diagonal cuts across the parallelogram. So that's one way you can do that freehand on paper and you can use a ruler. It helps out a lot to keep your things the same length and stuff. All right, well, that is how to add vectors. That's how they work in vector fields, like we used the electric field here. You could also use vector fields with like accelerations on a roller coaster or anything that's a vector. You could look at forces of gravity around planets instead of charges, and then gravity would just work with planets. Let's say like you have Earth here, and gravity would only attract in. So if you were to draw a gravity field around planet Earth, then it would always point inward. That's one of the weird things about gravity and electricity is that electricity can repel, but gravity always attracts. And so like a test charge or a test mass for a gravity field would always get a force pointed in towards it like that. If you put the moon out here or something, like the moon way out here, then it would have a smaller, which would have just less field lines there, but still extend out forever, but there's less of them to show a weaker field. And so then this little guy, this little test mass would feel a little bit of a pull directly into the moon, boop, but it's a weaker field and it's further away, and so it wouldn't be nearly as long. We draw vectors kind of proportional to each other to show that. And then what would the net effect be? Just move that head to tail again, draw the same length, and then draw from beginning to end. And so the resulting gravity force would be like this. You'd see your mass deflected a little bit, but still mostly falling into Earth. All right, well, thanks for physicsing with me, everybody. This was the Science Hutch. What was the Hutch? This was the science. You're the physicist. Keep on physicsing. Boom knowledge.